For having me. Sorry I could not be there in person today. And I'd like to talk a little bit higher level about 3D perception. So this is going to be a very quick sort of history, certainly not remotely comprehensive about SLAM, but a lot of the interesting developments started tackling individual elements at a time. So for instance, tracking, and then mapping or reconstruction, also some early works on semantic-based or object-based kind of SLAM. And then we saw more recently, because of the interesting developments in neural scene representations, that you could use learned representations also as scene representations for SLAM, as well as radiance field representations that allow for more of the appearance modeling, as well as this particular kind of scene representation. So I'd like to talk a little bit about some of the work that we're doing to hopefully provide some data that might support a more unified approach to this 3D perception. So bundling together information on tracking, reconstruction, semantics, appearance and view synthesis, and then hopefully also to be able to model things like interactions that are also very critical in a lot of robotics-oriented kind of applications. So the thing about this kind of data, certainly, and I think roboticists know this even better than those of us in 3D vision, is that the data is typically extremely limited. So compared to the text and the image or even the video domain, we have orders of magnitude less in terms of, let's say, real world kind of 3D scene data. On the other hand, from a pure learning perspective, that 3D representation actually potentially has some interesting advantages in allowing maybe conceptually for more efficient learning, because we don't necessarily need to relearn concepts like view consistency, temporal consistency, and stuff like this that you have inherently in the 3D representations. So this is kind of where I started working in this area, actually, on 3D reconstruction and semantic understanding. The challenge in this kind of setting, where we originally built a real-time 3D reconstruction framework that actually captured a lot of indoor scene environments, but you can see the quality here is a little bit not the greatest. So that makes it a little bit harder to leverage this kind of information as ground truth when you actually have this kind of noise and incomplete information to be able to learn good priors about indoor scenes. So more recently, my group has been developing the ScanNet++ data set, which is a high fidelity 3D data set that actually allows us to capture a lot of these kinds of characteristics. So you can see a similar kind of scan that we took, not exactly the same environment because there's a few years gap in between these two data sets, but a similar kind of style. And you can see the geometry is much higher fidelity, and that means that we have also a much easier time being able to label the semantics, especially of all of the small objects and the clutter in these scenes. And so we actually have about 1 millimeter resolution geometry from a laser scan that's being captured here, not just the geometry, but also high fidelity appearance. This is captured with DSLR compared to the older version of the iPad color camera here. And so this data set combines a couple of different modalities. Some of them are high fidelity and more like serving as ground truth. So this is the DSLR image capture for the appearance, as well as the geometry capture from a faro laser scanner. We also have the corresponding commodity sensor from an iPhone RGBD stream. And these are all registered together so that you have them all mapped into the same environments. So more specifically, these are the sensors that we used to capture this data set. We have about 40 million points per scan from the faro laser scanner, and then you go ahead and capture multiple scans per scene environment. The Sony Alpha 7 is our DSLR capture that captures nice images for the appearance synthesis. And then we have the commodity version of both depth and RGB from the iPhone 13 Pro. And so this is also a bit what the data capture process looks like. So here you see the geometry of the faro laser scanner, and also overlaid on top of that are the camera frustums from all of the DSLR capture. So the blue ones are train trajectories. The red ones are test views for novel view synthesis tasks. So we want them to be slightly out of distribution, so that we actually do understand whether when people try to model appearance of these kinds of scenes, whether they do have more true appearance model rather than interpolating through some kind of coherent existing trajectory. And here you can see a little bit of the visualization of the semantic annotations. Actually, this is still a non-trivial kind of process, but it's significantly easier when our geometry is much higher fidelity, because you can actually distinguish many of these sort of small objects in the scenes and actually label a lot of these individual instances much more easily. So here you see these individual plates all annotated in the semantic instance annotations. And this is to give you a bit of a sense of the appearance capture. This is a slightly older version of a view synthesis based off of the Nerfacto framework of one of the scene environments. And so this is also a novel view synthesis trajectory that's being rendered from an optimized radiance field representation for that particular scene. So overall, this data set has just over 1,000 scenes. We also have, to compose that, about 1.1 million DSLR frames and 10 million iPhone RGBD frames from the video. We also have 3.4K classes and 100,000 instances here. So this data set supports a couple of tasks, and we're hoping to include others as well. At the moment, we're looking at novel view synthesis, both from the high fidelity DSLR capture as well as the iPhone data capture. So currently this is our benchmark that is already been online since about half a year in terms of novel view synthesis for the new version of the data set. And just to give a bit of a sense of some of the methods that have been put on the benchmark, in terms of the DSLR capture, usually things look fairly good, but there can be some artifacts in challenging sort of reflective, refractive kind of regions. And then we also have semantic understanding, so both semantic and instance segmentation. These are the most common 80 classes by default that are being evaluated here. And you can see that the tasks can be also extremely fine-grained. So with instances, we have the individual books as instances for this particular task. All right. So with this, I think we can start to build some interesting kind of 3D priors that have this kind of holistic grounding into a lot of different data modalities and also potential downstream tasks. I did want to talk very quickly a little bit about some of the text and image priors, because of course, these from big sort of foundation models, as we call them these days, contain a lot of interesting information that's very generalized, but spatially weak. So typically, LLMs are notoriously bad at sort of 3D based kind of reasoning. So how can we incorporate 3D when we have a very sort of limited or almost no data kind of setting in this kind of area? In fact, we can formulate a 3D based optimization based off of some of these image generative models to be able to synthesize static interactions corresponding to input text prompts in a given sort of 3D scene environment. And this is leveraging some of the strong priors that we actually get from the 2D domain and being able to lift and optimize that into a 3D spatially consistent kind of setting. So I won't go into the technical details of this particular approach or the following, since we have a limited amount of time here, but we can also start to try to transfer this information of people interacting to humanoid robots, since the sort of kinematic and skeletal structure of a person is reasonably similar to a humanoid robot. So this setting, we have the task given as fetch the laundry basket. The scene is also given in this setting as this synthetic scene decomposed into the original objects. We do also have the individual subtasks here that are not shown, are given as input already, and we can leverage this synthesis or imagining of the human interactions and transfer that over so that we can optimize that into a humanoid robot to be able to perform this particular task. All right. So with that, I would like to conclude. I'm also happy to take any questions.
Thank you very much, Angela. Do you have any questions from the room? Okay, Michael?
Thanks for a great talk, Angela. Can you hear me?
Yes.
I was interested, you make the distinction in the data sets between the high quality DSLR and the consumer camera, and I guess I would think that that's increasingly a distinction that maybe doesn't matter as much anymore as consumer cameras get better. From your observations, what are the most important properties of the DSLR? Is it resolution? Is it dynamic range that differentiate it from the consumer camera for these sort of tasks?
Yeah, so from what we've observed, and we were targeting a lot of these appearance-based kind of tasks, there is still a huge difference between high-fidelity DSLR capture and like a standard kind of commodity phone. So it is true that like in the last couple of years, the RGB cameras on, let's say, like, you know, an iPhone or something like that have improved a lot. But there are still noticeable differences. I mean, most of the commodity color cameras are on a rolling shutter basis. They do have a significant amount of motion blur when you capture them in the video kind of setting. So the DSLR is actually captured from single photo snapshots, but at a very high frame rate. And that means that we can get a lot better consistency. We do also use them, I didn't mention this specifically, but we do capture the high fidelity setting in a slightly different setting because it's a high fidelity sensor. We use more, let's say, high fidelity information in the capture process. So the DSLR capture has actually been taken with the standard kind of settings you would use for structure for motion kind of captures, which is that we go ahead and calibrate the exposure and then fix all of these, like we turn off auto exposure and auto white balancing and all this kind of stuff, because that's what an expert can do when they go ahead and they want the best fidelity sort of structure for motion optimization results. It's also a fisheye camera. That helps a lot with the tracking. That's a bit orthogonal, though. These are, of course, though, not very common to find a fisheye camera on a commodity phone. And the iPhone capture, we try to capture in a more sort of casual capture style. So it's basically entirely the default video settings of an iPhone. So basically, white balancing, auto exposure, all that kind of stuff is on. And that can cause a lot more trouble in high fidelity optimization for structure for motion. Of course, you can get some reasonable poses because we have significant advances in that kind of domain, but there's definitely a noticeably lower quality than when you operate on the DSLR data, at least so far.
Thank you.